Okay, I am going to try a live proving session. And to start off with, let's see. I I had an in-class lab today for proving things, and I had bonus problems, which I had not actually done, which is not very good of me. So I'm gonna just try to do these. So let's see. The first problem that I had. Okay, so I defined like a version of reverse function. Um, and the reverse function that I defined that looked kind of different. Gosh, where even is it? Ancient reverse function. Ah. Here we go. Here's my reverse function. I defined it using tactics because I just wanted to kind of show people what it's like to use tactics to produce a term, kind of show the correspondence between these things. So yeah, here I have a different definition of reverse, which works very differently from my original one. And the thing that I asked people to do was to prove that the reverse function preserved length for this one, just like they did for the original one. Now, I think it's kind of interesting to look at both of these. They're defined very differently. Yeah, the first one is by induction, but it also works by calling out to the append function, whereas this one has an auxiliary function. Oh yeah, and then it's actually rev alt. That is the thing I want to prove something about. Okay, so let's just prove that. So we want to show that it preserves the length. Now I am going to do what I would usually do in this situation and just copy it. Why not? So I have this rev alt. Now I know ahead of time that this is almost certainly going to just fail. Well, that's the wrong reason that I would expect it to fail, but it's going to fail. And I'll explain why in a second, but we'll watch. Yeah, definitely failing. Okay. Looks like it dispatched the base case for me. Right, yeah, and so in the successor case, it's going to struggle, and I know why, which is kind of cute. So let's go up a bit. So yeah, so proofs kind of have to like mirror the structure of the functions that they're about kind of naturally. So when I wrote rev pres length before, what's really interesting here is that because our rev function calls out to append, because it's calling the append function, the like auxiliary lemma that we end up needing is about the length of the append function, and this is no coincidence. Like if you've ever written a recursive function that needed an auxiliary function that passed through something else, like here we have this like rev aux thing, then you've actually kind of done this like generalizing the inductive hypothesis thing that people talk about when they write their proofs, where like you don't have quite enough information here to write your proof. You know, it's like even if you unfold rev alt, does that simplify yet? Yeah, so you're just like, you get stuck. And you end up being in a place where you're going to have to prove something stronger. And it's actually the same exact thing when you get stuck here as it is like pulling something out into an auxiliary function. You're really like, now you're just defining an auxiliary lemma. And in fact, the structure of the auxiliary lemma is going to mirror the structure of your auxiliary function, which I love. So let's just make one like probably a rev aux pres length. I don't know. For all L1, L2, list A, length rev aux L1, L2 equals, I don't even actually know what it equals. So L2, if it's empty, rev aux is otherwise tail H consonant L2 is probably the sum of the lengths. We'll find out. So Actually, let's not intros first. Let's just, so we're gonna induct over L1 here. Why did I choose L1? So I choose L1 because this is actually the structure of our function. It's matching over L1. And there's this like deep correspondence between these things. So if I do this, I'll just intros there. This will give me two cases. Let's see what this is. It's probably like reflexivity. Yeah. And then let's go to the inductive case. Here, I can move this into the semicolon now, just to dispatch this case immediately if I'd like to. And now in the inductive case, what do I have? Simple. Probably want to rewrite by, let's rewrite by IHL1. It probably needs to be like that direction. And that's probably reflexivity. No, it's not. What am I doing wrong? Good, sometimes I mess up. Okay. For all L2, I see. Let's rewrite by IHL1 applied to a constant L2. I bet that's gonna work. Haha, that looks better to me. I would hope so. Okay, now I'm gonna need some lemma of some kind. But I don't want to figure it out, so I'm probably just gonna, I might have to import this thing. Yeah, I just called out to the like arithmetic hints to solve it for me, because I'm like, I don't want to reason about numbers like that. Although there's some cute stuff you can do if you want to figure out like which lemma I used. So, you know, it produces a term. If I look at the term, it'll tell me it is the plus n SM lemma. And we can even check that. So this auto with syntax here, you can pass in like a hint database where you store a bunch of relevant facts, and it's actually going to kind of use these facts to help you out, which is very nice. Oh wait, why am I checking that? That's incorrect. It'd be really fun to get a model to use the right hint databases. Okay, so yeah, here's the lemma that it used for us. So probably here, if we wanted to write it by hand, we could even just like apply, or maybe I have to rewrite, I don't know. Yeah, try that. I don't know why that emoji is. Yeah, now it would hold by reflexivity. But these things are sometimes more robust if you use like auto with arith, because if I change the lemma slightly, then it'll still work. Okay, so now let's go here. Now we're in our inductive case. And I bet this lemma is going to help us. So let's see. If we get simple, I'll unfold rev alt. And now we have this rev aux of a constant to L1 applied to empty. So let's just rewrite by our auxiliary lemma. Cute. What does that give us? More math. Actually, so like length of L plus 0 is not definitionally equal to length of L, which is an interesting thing. It's propositionally equal, but if you look at the addition function, it's kind of interesting. Print add, or is it plus? I don't even know. Yeah, it's add. So it matches over the first argument. So if your second argument is 0, it's just like it doesn't quite know what to do with this yet. So it can't reduce it for you. But I think we can probably just use auto with arith again. That would be my guess. Yeah. So you can see how useful these like hint databases can be. And there are a lot of other things, like there are some tactics specifically for math, like LIA for linear arithmetic. So if we look at this, we can see it used a couple lemmas here with plus n0. I don't want to print that. That's going to be ugly. No, no, no. Okay, check. Check will print the type of this. And yeah, so it used this lemma for us, which sounds really obvious, but it's actually something that you have to prove. Yeah, let's print it. Why not? You have to prove this inside of Coq by induction. Now it's kind of interesting. No matter which way you define addition, you're either going to have to prove the zero, the right identity, or the left identity of addition, and then the other one will come for free. Okay, so I also had this other bonus question that's prove that rev alt and rev behave the same. Lemma rev alt. Why not? For all L1, L2, no, for all L list A, rev alt L equals rev L, probably. Sure. Induction L auto. Let's see where that gets me. Simple. Probably doesn't work. Oh, it gives me something. Probably gonna need both of my auxiliary lemmas, I would bet. Rewrite by oh no, not these auxiliary lemmas. I might need auxiliary lemmas for both of these. That would be funny. I don't know. Let's see what lemmas I need. Rev aux L just A is equal to app rev L A. What is rev aux? Again, does it get me anything simple? I definitely am going to need to strengthen my inductive hypothesis here. Yeah. Now, what inductive hypothesis do I actually need? How are rev aux and app related? I think that's kind of the interesting question that gets stuck here. Oh wait, maybe I'm being silly because I can just rewrite. By this. What does that get me? That's cute. Okay, so maybe here I just need something about append. Is this my append function or is this Coq's append function? I don't even remember. Looks like it's my append function, which I define by induction. Okay, so wait, why am I doing that? App of rev aux L empty A is equal to rev aux L A. Maybe I need something like, let's see, what is this function? Probably something about the right identity would be good, actually. So let's do a list A of aux L empty is equal to, what is it equal to? maybe revox t. Let's see. Revox empty. It's just reversed. Oh yeah, obviously it is. That's what I can define reverse as. Okay, so revox L empty. I wonder what happens in the second argument. I don't even remember how I defined this function. Okay, well, that won't be that useful. So let's look at app. App of something with a single element should be equal to that element at the end of the list. 1, 2, 3, 4, 5. Revox. Okay, so app L1 applied to A. I need to eat. If I don't eat, I'm bad at proofs. Yeah, I definitely need some lemma relating revox and app, but I don't know what it is. But it definitely has to be stronger than this one. Although, I mean, let's just start off with this one and see where I struggle, because maybe that'll give me the lemma I want. Of course. I really don't need to make this complicated. I'm just moving that A out because cock infers this like inductive motive, and it just sometimes has extra things in it that I don't need. So now it's no longer for all quantified over A. So let's see if this alone gives us anything useful. It doesn't look like it. Oh, you know, maybe actually that inductive hypothesis was good. Yeah, I think the for all quantified one is kind of cute because you can do something like wait, but why do I need that? Yeah, it does. No. Yeah, it does matter. That is fascinating. Let's rewrite by IHL. Why not? Yeah, we'll definitely need lemmas about append app. Man, it's annoying that I used my append. I'm gonna do this the easier way because I don't feel like proving all these things about my append from scratch, and this is totally valid. So let's show that that our app behaves just like the one in the standard library. If you define its type correctly. Oh, I already proved that lemma. That's cute. Does it show the same thing? Yeah, that's hilarious. Okay, I already proved that lemma. That's a funny way to figure that out. Apparently, I am deterministic. Okay. Well, let's rewrite by app, okay. Let's do that before everything. Well, not that much before everything. Probably won't simple yet, but I think I have an idea. So now we can actually use any lemmas that are already defined of our app. That's what search shows us. Are there really that few things? Oh, these are my app. There we go. This is the standard library. It is cute. It's almost overwhelming. Someone brought up today like the need for a better search function. I agree. Some of these are just so irrelevant. Maybe commutativity is there? No, it's not commutative. Silly person. Is that true? No, doubtfully. Probability. Did I really just define a true theorem? I'm kind of surprised. Wait, L comes on to A. Yeah, okay. Apparently I defined a true theorem. Just one that is hard to prove still. Rev aux, rev aux. Let's try generalizing. Again, I don't know if this is true. Oh wait, this is just going to be exactly the thing I want, isn't it? Like in the end. Whatever, we'll figure it out. No, definitely not true. Wait, that's because I defined it incorrectly. This is interesting. Okay, what would I want? What is revox L1A? I just end up in the same place in circles over and over again. Okay. Yeah, so as you can see, thinking of lemmas that you need to prove is really hard. And I will rename these later. Maybe let's call this like revox cons. I did a user study once at proof engineers, and even experts would kind of write functions and proofs this way. I think today I'm kind of abnormally slow for myself because I'm tired and hungry, but nonetheless, usually when people fail their proofs, like 75% of the time that I observed, they would actually step back up and change something else, not the proof itself, which is really fascinating. I wonder if I even need this app whatever. I might be able to just use what I had in my proof down here. Revox cons, econs 1, 2. Revox L plus A. No, not yet. Okay, let's prove another thing then. Interesting. Right, so f equals, if two arguments are the same, then their function applied to them are the same, so I just get rid of that extra thing. And now I have reduced it to probably the same exact thing I wanted to begin with. Maybe let's try using this in whatever, because app whatever is probably too weak. So for sure, we're going to need something that generalizes over L2, and I think that's what I'm being silly. But I feel like maybe it's just that this is not what I want. Probably want something with rev aux and rev L1, and then I'm surprised by what. So list.rev L1 plus list. Oh wait, why am I using list.rev? Rev plus L2. Simple and star. Rewrite IHL1 probably. Why would I do that? Up with L1 to A. Wrong app. That's my app. Okay, that's why I was confused. Where's the distributive property or something? Or associative? Because I don't even know the right thing. Associative? There we go. Reflexivity, baby. Now I think I can use that more general thing here. So let's try that. Why am I repeating the same tactics? Gotta turn off the parentheses. No. Why is that called Revox comms? Silly Dahlia. I really don't feel like I should need induction here. I'm a little confused. Rev. Oh, that's because I have an extra argument there. Oh my gosh. No wonder, I just made it extra hard for no reason at all for myself. Now we can probably apply that nil R. No? Oh, because that's our own app nil R, and I want to use the real one in the standard library. There we go. So you can see how, even for me, for a lot of these proofs, I never just write them. It's like this interactive process of refining what I'm doing, which might just be reassuring. That's embarrassing.